In this video for section 6.5 of the text, we're going to see how we use integrals to determine the work done in various types of problems, lifting problems for the most part. So let's take a look at example 1 that is found in your textbook on page 129. So we're going to find the work done to lift a 500-pound motor that is attached to a 200-pound chain to the top of a 100-foot building, and we're going to assume that as we lift the motor and the chain that we're winding the chain up around, and so we're only lifting the part of the chain that is suspended. So first let's note that our formula for work that we're going to use is that the physics formula that work equals force times distance. And so in this case, a simple guess, which is incorrect, would be that the motor plus the chain weighs 700 pounds. We're moving it 100 feet, and so that would give us a work done of 70,000 foot-pounds. The problem with this estimation is that we're assuming we're lifting the entire chain, the entire 100 feet, and that is not the case. The weight of the motor is actually what, as a function of how high it is above the ground, the weight of the motor plus the chain is going to be 700 pounds minus the amount of chain that is sitting on the roof, and that amount of chain that is sitting on the roof is 2 times the amount that the chain is above the ground. So for instance, if when the chain is on the ground and x is 0, then we're lifting the entire chain plus the motor. When the chain is, or when the motor is 10 feet above the ground, we are lifting 700 minus 2 times 2 pounds of chain times 10 feet, and so we're only at that point lifting 680 pounds, and etc. So we have to have this variable formula for force. Excuse me, this isn't work right here, this is the force, which is the same as the weight. And so the formula that we have here only works when we have a constant force, which we do not have. And so what we have to do is use calculus methods. So let's take a look at how we do that on the next blackboard. So the work is going to be the sum of those constant forces of the changing weight of the chain times the amount the chain is moved. And so obviously when each time we move the chain or bring the chain up on the top of the building, the force or the weight of the motor plus the chain changes. And so this estimate right here is actually incorrect because it's not a constant force. But if we assume that the amount we move the chain gets smaller and smaller and smaller each time, so that delta x goes to dx, the summation sign goes to an integral, and the force is just the force that we have on a very essentially it's a constant force because we're only moving it a very small amount each time. And so we can then get this formula, which will give us the accuracy that we want. So let's set the problem up then. So the integral, or the work, is the integral between, well, let's put that in a second, and the force we said is what, 700 pounds minus 2 pounds for every foot we've raised the chain plus the motor up onto the building. So the initial value of x would be 0, and then when the all of the length of chain is up on top of the building, x would be 100, and so this will be our work formula. And when we integrate that, we get what? 700. So what? 700x minus x squared on the interval 0 or evaluate between 0 and 100, and that gives us what, 70,000 minus 100 squared, which is 10,000, which is 60,000 foot-pounds. And so we see that our initial estimate of 70,000 foot-pounds that we got back here was high, because we were assuming we were lifting the whole chain, and we weren't, and so this is the correct answer. Okay, so it's a little bit odd how we do this. We are only lifting a very teeny, or we're making the assumption that we're only lifting the chain very small increments dx, and so because when we make that assumption, then we essentially have a constant force, and we can use the force times distance formula. Okay, so let's now look at another example of where we're finding the work. And again, the issue is going to be that we have to use this force times distance formula. We have to have a constant force, so we have to break the problem down into smaller units so we can do that. So in this second example, we are going to find the work done in pumping all of the water out of this cistern. Here is the ground right here, so let's mark this as 0. The height of this cistern is 50 feet, and its radius is 20 feet. And what we're going to do is pump all of the water in it out to this level right here, to the top of the cistern. So to help us do this problem, let's take a look at another couple of pictures on the next blackboard. Okay, so the way we do this problem is to make the assumption that we can take a slice of water and move that water, which is at a height y above the ground. So this is y, and the entire height we said was what, 50 feet, the height of the cistern. And so we are moving that slice of water this amount right here, which is 50 minus y. And that slice of water does not have a constant force, because it actually weighs a very small amount. It weighs a little bit more on the top, where it has a larger radius, than it does on the bottom right there, where it has a smaller radius. But if we make that slice very, very thin, so let's actually denote its thickness, it is dy thick, then we don't have to worry about it having a larger radius on the top than on the bottom, or weighing more as we go from top to bottom. So what does the setup for the problem look like? Well, to do that, we actually have to draw another picture so that we can figure out what these slices, or actually how far we're moving these slices, and what the radius is as a function of y. So let's put one more picture in here. So if we take a cross section of the cone that looks like this triangle right here, that triangle, on that triangle we've got the radius of the slice, which is right here, so let's mark that as radius r, and that radius is going to give us the volume of that slice. So the volume of the slice is going to be what, pi times the radius squared times the thickness dy, and the radius To figure that out, let's set up a similar triangle relationship. So we've already labeled the height the slice is above the ground as y. We know that the height of the cistern is 50, and we know that across the top of the cistern the radius is 20. And so the ratio of the corresponding sides of the similar triangles, right? The big triangle right here is a similar triangle to this triangle right here. And so 20, the radius of the big triangle, actually let's do it differently. Let's put R, not the radius, but the leg, this leg right here of the enclosed triangle, is to the radius of the entire cistern, 20, as the y, the height right here, is to the entire height of the cistern, which is there, and which is 50, and that setup of similar triangles, corresponding sides of similar triangles, are proportional, right? And that allows us to solve for y and get this, that r equals 2/5 y, or 2y over 5. And so that allows us to determine the radius as a function of y. So if we go up to where we were here, we can write this volume as pi times 2y over 5 squared dy. So let's do the setup of the problem then. And so remember what we've got. We've got integral of the volume of the slice, which is pi times 2y over 5 squared, times the thickness of the slice. Let's put dy over here. And the weight of the slice is going to equal its volume times its density, and the density of water is, since this is water, we're pumping 62.4 pounds per cubic foot. And so let's put the 62.4 out here since it's a constant. And so the force and the weight are the same in these problems, right? And so let's mark here that everything we have on the integral so far is the force, representing the force. And now what we need to put in there is the distance. And the distance, if we go back to the previous slide, is how far that slice of water is moved, which is that amount, which we've already marked from here to here, and that is 50 minus y. So if we put that in, we now have, let me tag this just a little bit differently. So let's have everything, all the things multiplied together that represent the force, be in this green color. So that's the density, pi times the radius squared, and the thickness, and then the distance that slice is moved is that 50 minus y. So once more, so we're clear where everything is coming from. The volume of the slice of water is its cross-sectional area times its thickness. So that times that is the volume. And the density is right here. And density, and the density times the volume is equal to the weight, which is the same as the force. So So all of this portion times this portion represents the force. And it's force times distance if the force is a constant. If that slice is very, very thin, which is the case because we have a dy, then it is a constant. And then the distance that we're multiplying it by is right here, 50 minus y. Let's mark it here. Okay, so we have everything we need in the integral. The force times the distance. Right, the force is everything in the yellow box, and then the distance part is, let's tag it right here, and then there's the distance, 50 minus y. So we can, actually there's a missing part is, let's clean this up and go to that step. What are the limits of integration? Well, a slice on the bottom is going to move 50 feet. What value of y makes that distance 50 feet? Well, that would be 0. And a slice on the top is not moving any. And what y value would make the distance 0? That would be 50. So if we're pumping all the water out, we're moving slices at the bottom of the cistern 50 feet and slices on the top of the cistern 0 feet. So if you follow along as in your textbook on page 130, you see the calculations that we've taken the 62.4 and multiplied it by 2 over 5 squared, so it's 4 over 25 times 62.4 times pi. And then under the integral sign, we've got what, y squared times 50 minus y, or 50 y squared, which gives us, when we integrate it, 50 y squared integrates to 50y cubed over 3, and the y squared times the y that we have when we do this distributing of this, that's going to give us y cubed that we're integrating, and it's subtracted, so it's minus y to the 4th over 4, evaluated between 0 and 50, and the computations in the, are done for us in the book, and we see that we get what, this huge number, 16,332.282 foot-pounds. That concludes example 2. Notice that there's a slight, or a different, actually a pronounced difference in the way we set up these two problems in this pumping problem. The dy is necessary, making the slices very thin, so that we are moving a slice of a weight that is constant, and the dy is the thickness of the slice, whereas and we're moving that slice a distance, 50 minus y, whereas in the chain lifting problem, the setup was such that the way we made the force constant was to just move it very small increments, so that the changing weight of the chain was not noticed. So the dx here represented the amount it was moved, whereas over here the dx represented something, or dy represented something very different, the thickness, to make it constant. So we'll do some more examples of this type in the classroom and in the homework problems that you'll be doing. So this concludes this video on work calculated as integrals. I may add some additional examples from this section later in another video.